Alright, so we're back at Haskell. Missed out on a few days now, it was a little bit of chaotic stuff. But let's now finally start looking at recursive data structures. Which just sounds weird, but we can have functions within our data structures, right? That's kind of what we've been learning. So of course, we can have functions within our data structures. We can have values, we can have functions, of course, we can have recursive ones, I suppose. As we've seen, a constructor in an algebraic data type can have several or none at all fields, and each field must be some concrete type. With that in mind, we can make types whose constructors have fields that are of the same type. Using that, we can create recursive data types, where one value of some type contains values of that type, which in turn contains more values of the same type, and so on. Colgatinotab says, I heard you liked data structures, so we put data structures in your data structures, so you can structure your data while structuring data. Exactly. Oh man, that's lovely. Yo, dog. Alright. Actually, Colgatinotab, I think you put it better. This confused me, but I like that one better. Yeah. Think about this. Think about this list. Yeah, that's just syntactic sugar for 5 into an empty list, yeah. On the left side of the colon, what do we call this in Haskell again, in this context? Put into operator. Oh man, I just had this vision of some nerd having sex with his girlfriend and just saying, I am the put into operator. I don't know. made me laugh anyway. There's a value on the right side, and that's a list. And in this case, it's an empty list. Now, how about the list 4 and 5? Well, that desugars 4 into 5 into an empty list. Look at the first colon. We see that it also has an element on its left side and a list on its right side. Same goes for lists like this, which could be written like this, which is a mess. That's like Lisp. Or we can write it like this, shiny Haskell. Very nice. Colgatinotab says that sometimes things are easier to explain with memes. Yes, they are. Right, because colon is right associative. Because people are already familiar with memes? Exactly. That is good. And I think this book is older than that meme, maybe? Yeah. Also, I wouldn't put memes in a book because, right, you don't want to be dependent on outside cultural phenomenon when you're trying to write a teaching book. That would be weird. Hello, Nodrunner. Nice to meet you. He says, hi, I'm new. Yep, never been here before. Definitely not. Well, it's nice to meet you the first time. I hope you're interested in Haskell and interested in jumping in midpoint in Haskell, yeah. Man, I just got this feeling, you know. Sometimes I get this. I'm a little bit, what's that word? Clairvoyant. I just got that feeling that you just took a nap. Yeah, you just woke up from a nap. How was your nap, if my clairvoyance is working? Right, we could say that a list can be an empty list, or it can be an element joined together with a colon with another list. That can be either the empty list or not. Let's use algebraic data types to implement our own list then. Okay, We do data, we do list A, which can be an empty list, or it can be cons. Is that the name of the colon thing? Cons A onto list A. Yep. Here's the recursion. That's how we do it. Just put the A... Damn it, I can't say put it into A. There was a joke in there, but nope. Slider McMentalist. I feel better now, says Snowdunner. Great. Right. Naps are good for you. Naps are good for you indeed. Yeah, I really like that dude. The Mentalist. What's his face? I'm so bad with names. The British dude. You know the guy. Skinhead. Darren Brown. Yeah, I highly recommend watching some of his live shows. They're on YouTube. Darren Brown. He's kind of cool. If you're into magic and hypnosis, it's kind of cool. I like that he's a magician that just goes out and he's not even trying to have a veil of actual magic and whatnot. No, he's just straight out telling people this is not real. We're just making it up as we go along. Very scientific in his explanation of what is going on. I remember I saw a show where he did faith healing. Right, and faith healing is... He was kind of pointing out because he doesn't like mediums and whatnot. So he was saying, right, this is all bullcrap, right? We're not religious. I'm not religious. We're not invoking any god. But let's try it anyway. And he managed to do some faith healing. It was kind of cool, yeah. Now, says, if hypnosis is real, it is because you're hypnotizing yourself. Well, it's more... I mean, suggestion is real. I think suggestion, like if you put it like suggestion instead of putting it like hypnosis, it makes a lot more sense what is going in, right? Going on. Sorry. I'm all about putting stuff in today. I don't know. Like a teenager. So, right, suggestion is definitely a real thing, right? Priming and whatnot, that shit just works. So, hypnosis is just where you get manipulated to be in a state where you're extra ready to be suggested to, right? I remember I saw an interview with him, right, where he said, I don't know, right, if the people that I hypnotize, if they're just playing along, or if they're actually not knowing what's going on, right? It's pretty straightforward with that. He can't say. Some of the things that he gets people to do under hypnosis seems really weird, but at the same time, it's like, yeah. The thing that he knows is that it works. I think it's because they believe it and play along. Probably, yeah. I think, and I heard him say that as well, it doesn't work on everybody. Right? Some people are just more easily suggestible than other people, and that's just like everything else. You put stuff on a normal distribution curve, right? When you have stuff that people are good at and bad at, or stuff like that. Colgate says that Nora Karma is a pretty good Finnish mentalist, but she didn't see her husband leaving her coming. Savage, dude. Maybe she did. It was for the best. Does she do it in Finnish, or is it like... I don't know if I'm interested in watching Finnish mentalism, but I don't know. Right, where were we? This reads just like our definition of lists from one of our previous paragraphs. It's either an empty list or a combination of a head with... my head is in the gutter today. With some value and a list. If you're confused about this, you might find it easier to understand in record syntax. Or what the record was, right? It's either an empt or it's a cons list head. Oh, wow. Right. That's our data structure. It's either an empty list or we put... This actually confused me more. Oh yeah, we put the list head. That's A, and we put it into our list head. Wait, I'm super confused. Multi-continuum tab says usually Finnish, sometimes English. Might be worth checking out. I'm gonna write it down. Make a quick check myself. Nora Karma. Yishin. I haven't watched any Magic in a while, and I find it quite enjoyable when it's done as good entertainment, yeah. Right, you might also be confused about the cons constructor here. Cons is another word for the colon. Yep. That I figured out. The cons is the colon thing, yeah. You see, in lists, colon is actually a constructor that takes a value and another list and returns a list. We can already use our new list type. In other words, it has two fields. One field is of the type A, and the other is of the type a list of A. Right, so this is not a function. This is a constructor. Yeah. Empty, alright, we have something empty. Alright, that was what we had, yeah. And then we put 5 into our empty, so we have 5 empty. And then we put 4 into, yeah, what we have. Right, this is our list. Just very different syntax. Yeah, our syntax is different. We called our cons constructor in an infix manner, so you can see how it's just like the colon. Empty is like the empty list, and 4 cons to 5 cons into empty is like, yeah, exactly. It looks exactly the same, but ugly. It's less readable because they're doing the Lisp thing with the parentheses. We can define functions to be automatically infixed by making them comprised of only special characters. We can also do the same with constructors, since they are just functions that return a data type. So check this out. Infixer. Wait, what is this? Data list A. It's either empty or, oh, we're just doing the same. We're doing a list again. Yeah. Well, Gitino tab says, well, constructors are functions. Right. Yeah. It is a function, but it is a because of it being in here. Since it's in our data thing, it's a constructor. Shit, I forgot. There were 2 types of constructors, right? Oh, man, I don't remember that. We had... Is this the type constructor? And you could put a constructor in here as well. Oh, this is a construct... Shit, I don't remember. Right, I probably won't be creating my own data types for a while though. I feel like this before hello world is weird. Too much theory. Yeah, the theory is way ahead the practice. For me personally, yeah. Need some more practical exercises. Doing some more code wars. Later though. Alright. First off, we notice a new syntactic construct. The Fixity Declarations. Oh, is this the Fixity Declaration? When we define functions as operators, we can use that to give them a fixity. Terrible name. But we don't have to. A fixity states how tightly the operator binds and whether it's left associative or right associative. For instance, the multiplication is fixity is infix L. Oh, right. That's infix right. Infix L. And pluses in fixity is infix left. Yeah. That means that they're both left associative. Right. 4 multiplied by 3 multiplied by 2 is 4 multiplied by 3, and that whole thing is multiplied by 2. But multiply binds together tighter than plus because it has a greater fixity. Wait, how do we know the greatness? Oh, is that the number? How like... Yeah, order of operations, right? Yeah, so 5 multiplied by 4 plus 3 is exactly. Otherwise, we just wrote a colon dash colon list A instead of cons A list A. Now we can write our lists in our list type like so. Right. We'll get in on tab says, well, if that's what you need, I said later. All right. We'll taking a short break from this reading, I guess, and doing a kata. Hopefully it'll be as fast as the other ones, yeah. Outrunners is still thinking about names over here. Nice. I got playable. Playable. Nice. That's a great name. But I'm not sure if playable is good or not. I think that's amazing. Right, to put in context, my clairvoyance is telling me that NodeRunner is having this idea of building mods for games to make them more... What's that word? There's a word I'm looking for. Shit, I'm tired today. Playable for people with disabilities, right? So, playable, a great name for that kind of, if you're trying to make build a group or a movement, right? Where you make mods to make games more playable for people with disabilities, right? You could have mods that add different shaders or whatnot for people who are colorblind, so the game become more playable. Oh, I love that. Node says, also, I don't just want to focus on disabilities, because anyone can make use of these features. Yeah, exactly. Like highlighting stuff in your environment. That's good for anyone. You don't have to be colorblind to have a use for highlighted stuff in your games. We'll get in tab says to NodeRunner, did Cider got it right? About the playable or playable thing. What do you mean? Let's see. Code Wars. Right. We interrupt this reading of types and type classes by hopefully making a quick kata here in Haskell. See if we can do this. Alright. This is an easy twist to the example kata provided by Code Wars when learning how to create your own kata. Oh, I don't remember that. Add the value code wars to the array. Array? Websites. Websites 1,000 times. Wait. Oh, in some places it's called website with a capital W, and other places it's called... Right. Depends on what language you're doing, I guess. So I suppose what we do is just that we... Did it repeat? Like, I don't remember the name. Is it repeat? Repeat. And then we just... let's see, what was it? Code wars. Repeat. Code wars. 1,000 times. Is that how we do it in Haskell? Test. Function repeat is applied to 2 arguments. Oh, you have the number first, maybe? Yeah, repeat 1,000 times. Code wars. No, that's not it. Oh, the clairvoyance working. Right, about designing stuff. Yeah, he's got some really good magical powers. Ooh, I'm so magic. Alright. Couldn't match expected type. Oh, it tries to repeat a character. It cannot repeat a string. Alright, let's check this out. UHCI repeat. No, it takes something and makes it into a list. But it doesn't take a number. Maybe it's not the function that I'm thinking of. Since I'm terrible with names. Well, Untitled says it complains about the amount of arguments, not about their order. Yeah. It just takes 1 argument. But repeat code wars. How do we get it to be 1,000 times? So I'm just doing the wrong function, aren't I? Oh shit, it's... Yeah, execution timed out. It just this is... Oh! It does it infinitely. Yeah. Like that? Does that work? There it is. Yeah. Repeat does it infinitely. There is another one. I know there is a better solution to this, but there we have it. That's one way of doing it. Repeat just does it over and over and over again. I know that there is a function that does the equivalent of this. I think there is anyway. We'll see what the other one says. Replicate. Man, that's such a good name. Yeah. Replicate. Oh, man. I did love Stargate SG-1. The replicators got out of hand after a while, but wow, look at this. Are you kidding me? This is the best solution. Oh man, that was hysterical. This person wins. Clever indeed, yeah. Alright, I gotta start voting on these things. Wait, I can only vote for either clever or best practices? Oh, yeah, it's clever. That's funny, yeah. Right. Outrunner is using this as his new avatar. Right. Oh shit, like that. No. Shit. Why not? There we go. That's his new avatar. That's pretty cool. It's made by Artbreeder. Yeah, that's a cool website. Artbreeder. It just makes art. You can make art on the internet if you use Artbreeder, indeed. Peak coding right there, says Colgate in on tap. Yeah, right, yeah. Not only says you might not like it, but this is what peak coding looks like. Nice. It would have been even better without the syntactic sugar. Yeah. Would have been even better if we did it like this. Yeah. What was it like? Code Wars. No. Wait. And right. Code Wars, and then. But we could make it even worse, right? We could make it even worse. We could do something like this, right? Actually, let's remove those. Oh man. Look at this. Right? No syntactic sugar. Oh man. I mean, you see where this is going, right? I mean, yeah, you see where this is going. Holy shit. Oof. Not only says it took a lot of work to make this, believe it or not. The Artbreeder thing. Oh, I believe it, yeah. That was good looking. I can imagine you spending a lot of time on that. Definitely good looking. Right. Hello, Solbaron. Nice to see you again. Syntactic sugar is nice. I agree, yeah. Syntactic sugar is very nice. Can make that look really awful. Right. Alright, let's see. Now we can write our lists now we can write out lists in our list type like so. Yeah, exactly. They just made it this. We're just re-implementing list here to understand how. What was this called? Syntactic construct. Yeah, we can decide if it's an infix, we can decide if it's a prefix, and we can decide where it's associative and how strong it is. Pretty good. Solburn 666, especially do notation for monads. I mean, I've been doing this for 3 weeks, more than 3 weeks now, and we still haven't reached the monads. Maybe I'm slow? It's fine if I'm slow, yeah. When deriving show for our type, Haskell will still display it as if the constructor was a prefix function, hence the parentheses around the operator. Remember, 4 plus 3 is parentheses 4 and 3. Why does it do that? Is there a reason for doing this? That's kind of, I remember that when we learned about the prefix and infix, and I said, isn't it better to just have all of them as prefix? I've changed my mind, but it kind of looks like that is actually what we're having. All of them are prefixes, but we have, the infix are just syntactic sugar, and I'm assuming implementing show with syntactic sugar in mind is probably inefficient, maybe. You can always use them as prefix. No, I remember, and you can always use them as... No. You can use them as infix if they take 2 parameters. Let's make a function that adds 2 of our lists together. This is how ++ is defined for normal lists. It's an infix right, 5 again, ++, alright, and then we have our ++. Yeah, we have to put the parentheses to treat it like the prefix. List and another list, and we get a list. And if we have an empty list, then we, right, join together with our list, then we just get, wait, which one is ours? It doesn't matter, right? We have two parameters. Otherwise, we just do it recursively. Take the head. Wow. Under the hood, it's a mess, yeah. There's no hours in Haskell, no self, or this. Oh, I mean, hours, like mine. I'm like the... I have a list. When I use this function. Actually, I have two lists. Yeah, both these lists are mine. Yeah. I have two lists. And... right, if one of them is an empty list, then we only get the rest of the list. Thus the... oh, and it's right associative. What if we flip sides on these? Does that matter? No, it doesn't matter. Right, because we take the head... it's because we're making... yeah, we're making a recursive call. The plus plus is a recursive function. Look at that. Recursion everywhere. Right. So we'll just steal that for our own list. We'll name the function dot plus plus, eh? Yeah. Right, infix, right? Alright, we're just doing the exact same thing, aren't we? Yeah. Doing the exact same thing. Just with different wordings. And different syntax. Solburn says specifically tail recursion, which optimizes away. Oh yeah, tail recursion is everywhere. Wait, what optimizes away? The optimizer optimizes away. Yes, there we go. And when you say the optimizer, that is something within the compiler, right? There is an optimizer within the compiler. Is that how it works? And let's see if it works. Oh, lo and behold, it works. We have a list, and this is how a list looks. Solburn says, yes, it's part of the compiler. Very nice. Right. Nice is nice. If we wanted, we could implement all of the functions that operate on lists on our own list type. If we wanted to, we don't want to. Yeah, no. Notice how we pattern matched on XXS. Wait, where did we do that? That works because pattern matching is actually about matching constructors. We can match on our put into list function, well, data constructor, I guess, but because it is a constructor for our own list type, and we can also match on colon because it is a constructor for the built-in list type. Same goes for the double brackets because pattern matching works only on constructors. We can match for stuff like that normal prefix constructors. Oh, wait, we can match for stuff like that normal prefix constructors or stuff like 8 or a, which are basically constructors for the numeric and character types respectively. Now we're going to implement binary search tree. If you're not familiar with binary search tree from languages like C, here's what they are. An element points to two elements, one on its left and one on its right. I'm not familiar with binary search tree. The element to the left is smaller, the element to the right is bigger. Each of those elements can also point to two elements, or one or none. In effect, each element has up to two subtrees. Actually, isn't this... No. we'll get to it, right? Binary search tree. And the cool thing about binary search trees is that we know that all the elements at the left subtree of, say, 5 are going to be smaller than 5. Elements on its right subtree are going to be bigger. So if we need to find if 8 is in our tree, we'd start at 5, and then because 8 is greater than 5, we'd go right. We're now at 7, and because 8 is greater than 7, we go right again. Yeah. And we've found our element in 3 hops. Now, if this were a normal list or a tree, but really unbalanced, it would take us 7 hops instead of 3 to see if 8 is in there. Right, this makes sense to me. I've never worked with these types of data structures before, like at all. Oh man, here it is, yeah. Oh man, the colors are all bright, but yeah. This is how you do it. This is peak coding. Right. The thing is though, I'm pretty sure you cheated. You made a program to do this, you didn't type it out well. Peak coding. Oh man, it's awful. It's awful, I'm telling you. Hello, Coleman. Nice to see you again. How are you doing? What is this wall of yellow? Right, that's peak coding. That's how you do peak coding in Haskell, yeah. Oh man, that was awful. Not only the way it was structured, but the colors as well. So how are you doing, Coleman? Now it's 7, because that is greater, we go... Yeah, exactly. This handy little image shows us exactly how this works, a binary search tree. More like peak eye damage? Yeah, exactly. Doing fine? Good to hear, yeah. Well, Get In on Tab says, well, your add-on messed up colors. I hear excuses. I hear excuses, yeah. Not Owner says, looks like how better Twitch TV is coded. All right. Man, immediately, eh? Immediately. What's that? Flame Wars? Right, yeah, that's Flame Wars. I think that's what they're called. Sets and maps from data.set and data.map are implemented using trees. I remember them talking about that, yeah. Only instead of normal binary search trees, they use balanced binary search trees, which are always balanced. Okay, but right now we'll just be implementing normal binary search tree. Here's what we're going to say. A tree is either an empty tree or it's an element that contains some value and 2 trees. Sounds like a perfect fit for an algebraic data type. Is it? Yeah. Code Wars? Oh, right, yeah, we did do some Code Wars. Actually, that's a good name for it, yeah. Yeah. My language is the best. Oh, my language is the best. Good times. Drama. Drama-inducing. Right, let's do this this sentence one more time. Here's what we're going to say. A tree is either an empty tree, that makes sense, or it's an element that contains some value and 2 trees. Sounds like a perfect fit for an algebraic data type. Right. So it's either an empty tree, or we have our 5 here, and it contains 2 trees. This tree and this tree. Right, and since one of the trees can be an empty tree, we could have like let's pretend that 8 here doesn't exist. Then we could have, it contains its node 7, and you could have the tree 6, and you could have an empty tree, right? If we imagine that this 8 was just not here, right? Yeah. Right, so that's how we do it. And right, it is recursive. Makes sense. And we derive show read. Man, this is when the data structures are starting to look powerful. I find it weird that I've never gotten into this type of data structure before, because, oh man. Powerful stuff, isn't it? Fairly easy to define the data structure as well. It's very similar to the list, right? How did we implement the list? Let's go up here. Okay, we had a value and then we put it on the list. Yeah. Very similar, but it's like we have a list like this, and we have a list like that, and we have a list. Very interesting. Okay, good. This is good. Instead of manually building a tree, we're going to make a function that takes a tree and an element that inserts an element. We do this by comparing the value that we want to insert to the root node, and then if it's smaller, we go left. If it's larger, we go right. We do the same for every subsequent node until we reach an empty tree. Once we've reached an empty tree, we just insert a node with that value instead of the empty tree. Oh man. Take that one more time. We're going to make a function that takes a tree and an element and inserts an element. Right, we compare the values. We have our elements. If it's smaller, we go left. Wait, if it's smaller than this one, and if it's bigger than this one, right? We don't check for equality. Right, if it's the same, we haven't dealt with that yet. Yeah. Oh, really? Node owner says I got a response from Stallman. Did you? Was it an automated response? I get a lot of emails right now, and I can't be bothered to answer all of them. Oh, yes? That sounds interesting. No, it's a real response? Wow, he's fast at responding to emails from strangers. That's pretty cool. Yeah, that's pretty cool. To me, it feels like a person that's like far removed and have way more important stuff to do than to answer emails from some random person on the internet. So, did he notice your troll, or... I mean, I'd love to hear this response, hear about this response. In context, right? Yesterday we were talking about Stallman and his likeness being used in proprietary software, right? There's a lot of stuff you can buy with Stallman's face on it in Steam. He said, alas, I can't access those pages. Could you show me what you mean and explain what you're talking about? Oh, right. Yeah, he can't go and see those pages because those are not accessible when you're hardcore free and open source software. Yeah, can't go into Steam pages. That's unacceptable, isn't it? Yeah. Colgate InnoTab says, but Node Runner is not just any stranger. Node Runner is a new stranger. A very good point. Right. We do the same for every subsequent node until we reach an empty tree. Once we reached an empty tree, we just insert a node with a value instead of the empty tree. Right? This makes sense. Oh, right, but we create a... It's like an edge case. If we find our value in one of the trees, then it's like, whoop, stop, we're not doing this. Probably. I'm assuming that is what's gonna happen. Right, I'm assuming you're gonna take pictures, Node Runner, and send them in a response email and show him. Right? You showed us pictures yesterday. It's just you can just take a screenshot of what you're looking at, right? In languages like C, we do this by modifying the pointers and values inside the tree. In Haskell, we can't really modify our tree. So we have to make a new subtree each time we decide to go left or right, and in the end, the insertion function returns a completely new tree. Yeah, because we're a lazy language, right? Yeah. And imgur links of pictures, yeah, that's gonna work. Colgatin on tap, yeah. I might have to take Polaroids and send them in actual mail at this, right? Wait, really? Can't you just mail normal JPEGs? Doesn't that work? Can't you look at JPEGs in free and open source software? That works, doesn't it? Take Polaroids off the screen. Oh man. Oh, that's hilarious. Right, because Haskell doesn't really have a concept of a pointer, just values. Hence the type for our insertion function is going to be something like a... Alright, we have our value, and we have our tree, and we return a tree. Yeah, exactly. Takes an element and a tree and returns a new tree that has that element inside. This might seem like it's inefficient, but laziness takes care of that problem. Yeah, exactly. That was what I was thinking. It doesn't seem inefficient because it's lazy. That's one of the benefits of functional programming. You can have, just like you can have infinite lists, you can have infinite trees. Yeah. Node owner says, I don't know. He might find some reason why JPEGs are not kosher. I mean, I don't think so. Well, you're going to love this. Alright, what next? Node owner says, at the top of his email it says, to any to any NSA and FBI agents reading my email, please consider whether defending the US Constitution against all enemies, foreign or domestic, requires you to follow Snowden's examples. Lovely. That's very US focused, right? I can imagine, well, I don't actually well, Stallman's emails could be interesting, I guess, to read for people, but I don't think actual human beings are reading these emails. I think it's just machines reading the emails, right? Oh man. Defending the US Constitution against all enemies, foreign and domestic. Oh, wow. Oh. You're right, I did love that. Stallman is hilarious. This might seem like it's... No. Laziness, good stuff, yeah. So here are two functions. One is a utility function for making a singleton tree, a tree with just one node, and a function to insert an element into a tree. Right. So a singleton... Wait, why do we have to do a utility function for this? Right. Singleton x, right? We take a value and our node becomes our value and we got an empty tree. Oh, because this is how you implement your data type. You have to... I can't just... Yeah, I can't just decide... Right. Right, tree insert, right? We take something that is or in the ORD type class and a tree of that same type class, and we return a new tree with that type class. All right. If right, our edge case is that we tree insert our value, and if we take our value and have an empty tree, that's when we return a singleton. Oh, right. That's when we insert a singleton into our tree. It's just a value. And otherwise we do a guard thing, right? We have our value, have our... Wait. This is confusing. We insert our value, and then we have... Oh, this is our tree? Oh yeah, node, left, right. Exactly. This is our data structure right here. Right, we take our value and we take our tree. This is our tree. So, if x is equal to... Oh, right, that's what I was asking for. If a is equal to a, we go... Node x left, right. Oh, we do nothing, right? Yeah, we just return our tree. Yeah, that's an edge case. If we find this, we just don't do anything. We just return our current tree. If x is smaller than a, then we do... Shit. Then from our node, we insert to our left. Yeah, we insert x to our left. Just keep the right. And if we insert it to the right. Man, it's way easier when you just look at it like this. Here, it becomes a little bit confusing to keep track, but it's... Well, this syntax is confusing me a little bit, but we know what we're doing. Yeah. Since the naming conventions are here, right? We insert to the left if it's smaller, and we insert to the right if it's bigger. There we go. Colgate in on tap asks, do you like trees? I love trees, yeah. When I go outside, one of my favorite things are trees. I like the leaves, I like the structure. I like to imagine, or I like the idea of evolution, right? That a tree is pretty much, that is how our brain is structured. A tree's structure, where it sprouts out new branches all directions, that is how our nervous system works. We started out with the spine, right? And then we sprout out neurons in all the types of different directions, just randomly, right? Evolutionary wise. And from that we build the whole structure that is the brain. It's like the crown of a tree, where it just goes and does all of the stuff. I like that similarity, that comparison between life and life. And you can see that same structure. I don't know, I think it's cool. Noterunner says the problem with responding to his email is he left things so open-ended that I have no idea what he wants me to tell him. Send him pictures, Noterunner. That's exactly what you're doing. Yeah. Right? Yeah. Could you show me, that's show, pictures, or it didn't happen, right? Show me what you mean and explain what you're talking about. So show him the pictures and reiterate what you were saying on the first mail, right? This is proprietary software, and these images are sold within this storefront. Yeah, there we go. Colleague Din on tab says, I think he wants you to tell him. Exactly, yeah. Colleague Din on tab is asking for some inspiration, so close your eyes and take a deep breath. In. and out. We can do it one more time. In and out. Node says, yeah, I got that part. So was it really that open-ended? To me, it looked pretty straightforward. Right, the singleton function is just a shortcut for making a node that has something and then two empty subtrees. In the insertion function, we first have the edge condition as a pattern. Yep. If we reached an empty subtree, that means we're where we want, and instead of the empty tree, we put a singleton tree with our element. Exactly. If we're not inserting into an empty tree, then we have to check some things. First off, if the element we're inserting is equal to the root element, then just return a tree that's the same. Yep. If it's smaller, return a tree that has the same root value, the same right subtree, but instead of its left subtree, put a tree that has our value inserted to it. Same, but the other way around goes if our value is bigger than the root element. Yeah, exactly, right? Here is, if it's the same, we just return the same, because our element is already in the tree. So that's what we do. We insert on the left side in our tree, we make our insertion. But we keep the right version, right? And since it's recursive, we go down, right? Let's say 8 wasn't here and we were inserting 8, right? What we do is that, okay, we just copy this, right? We keep it as is. We keep the left, and then we go down the right. This is our recursion move right here. We take on this tree, we call our function again. We do the same, we keep the left one, and we go to the right. And here is our empty tree, right? So this is where we insert our singleton to create our 8. Yeah, it's this one though, yeah. We keep the left as it is, and we insert our x, our tree, or our empty node. No, our singleton, sorry. We insert our singleton at the edge condition, right? Because sooner or later we will reach our edge condition, and that is when we insert our singleton. There we go. Node owner says, I don't know if you know what Valve is, what Steam is, what video games, what a video game is, what an emoticon is, why people would buy an emoticon. Actually, I'm starting to wonder that last part myself. I don't fucking know, dude. I've never bought one. There are probably a multitude of reasons why to do that, yeah. Part of it is to make your own profile, part of it is to make chat stuff. There's probably some messing around with the market, the Steam market, and you make money by selling and buying stuff, right? Manipulating, so you get free games, yeah. I mean, let's assume that he knows what a video game is. Yeah. You don't have to explain what an emoticon is, because it's just an image of his likeness that is being sold. And he knows what that is. It's a picture that's being used within this certain piece of proprietary software, right? So he doesn't need to know. He knows what a platform is. I'm pretty sure we've read some of his papers and he knows what a platform is. I mean, you could just make an example and send a smiley on your email and explain, right? Instead of being the colon parentheses, instead you get a small image. And those are being sold. Right? Like an email platform, I don't know. Tab says, I read that as what emotions are. What an emotion is. Emoticon makes more sense. It does indeed. Tab says, no. One more recursion for the empty tree. Wait. Isn't this our last? Right? We insert, we have our value, and oh, it turns out we have an empty tree. We insert our singleton, and then we're done, right? That's the last recursion, right? Because, yeah, it goes down, but here we're done. We won't ever go down here again. So this is the last recursion, right? Another says, why would people buy an emotion? Oh wait, that's what drugs are for. That's what buying all the decadent stuff is for, right? Buying culture. Reading a book. Did you buy a book? Just buy a house and you'll get the feeling of safety. Yeah, you get an emotion where you feel safe. So just buy a house, it's that easy. Like, a lot of buying is about buying emotions, yeah. Not only drugs. Well, Gitinotab says, when you used your picture, you still had the 8-node empty tree. Oh, right. I wasn't clear. I was imagining that this node was not here. I was imagining that this node was not here, and this was the node that we added to our tree. Sorry if that wasn't clear. But yeah, if the 8 was here, then we would have gone down again. Let's say if we did insert 9, we would have gone down here, and we would have gone down and put a 9 down here, right? Yeah, it would be right because it's bigger, and we would have an empty tree down here. It wouldn't be anything down here. Yeah, this tree would never ever exist instead, unless we started putting floats in, I suppose. Colgate In on Taps says, I thought drugs were for experience. Or getting healthy. Yeah, and those experiences you get for having emotions, right? Healthy, you want to feel good. So you try to get healthy, right? Right, so now it makes more sense when they explained it to me. I like that. Next up, what time is it? How far do we have to go in this little chapter? Actually, let's take a little bit of late lunch today and go down to type classes 1.2 and do that tomorrow. Next up, we're going to make a function that checks if some element is in the tree. First, let's define the edge condition. If we're looking for an element in an empty tree, then it's clearly not there. Yep. Okay, notice how and this is the same as the edge condition when searching for elements in lists. It is, yeah. If we're looking for an element in an empty list, it's not there. Indeed. Anyway, if we're not looking for an element in an empty tree, if we're not looking for an element in an empty tree, then we check some things. If the element is in the root node, it is what we're looking for. Great. If it's not, what then? Well, we can take advantage of knowing that all the elements are smaller, all the elements to the left are smaller than the root node. So if the element we're looking for is smaller than the root node, check to see if it is the left subtree. If it's bigger, then check to see if it's in the right subtree. Exactly. We don't have to look through our entire tree. That's... yeah. So our recursion only happens... yeah. It's like when someone says to you, I'm thinking of a number between 1 and 100. And I will only answer if my number is higher or lower. You always split the middle, right? You ask, is your number 50? No, it's higher. All right. Is your number 75? No, it's all right. Like you see, it's the same kind of structure. It's the fastest time to find something in a data structure like this. Colgate In on Tab says, so the ultimate goal is still emotions? Kinda. Not always emotions, but we are an emotional species, Colgate In on Tab. Most of our actions are based on the striving for the achievement of some kind of emotion, right? Not all of it. Right? We're not there's not only emotional stuff, but most of our behavior can be derived from emotional cravings, yeah, one way or another. I think that's, a lot of people make that mistake and think we're a rational species. And, I mean, we're, compared to all the other animals, we're pretty good at rationality, but at our core, that's not what we are. At our core, right, the reason we strive for rationality, you can oftentimes find like an emotional driving force within a human, right? Yeah. That makes sense. That's why we have them, the emotions. They drive our behavior. That's why they're there. Their ultimate purpose is to drive behavior. Colgatinotep says, or are emotions yet another tool for an even grander scheme? Yeah, right. You take an evolutionary perspective, you say, well, it's because we're driving behavior, right? And it's for driving behaviors that ultimately are good for you for one reason or another. A lot of people get stuck on the survival thing of evolution, that it's about staying alive, and sure, that's it. But we have other driving forces as well. Ah, what's this? Sorting algorithm for 6 minutes by Timo Bigman. Visualization and audialization. All right, let's... Sorts. Random shuffles of integers with both... Oh, speed and... Alright. This is an 15 sorting algorithms in 6 minutes. Alright, it's a visualization of different sorting algorithms. Fun. And that's not what we're doing right now. We're finding something. We're not sorting right now, are we? I don't think so. Alright. All we had to do was write up the previous paragraph in code. Yeah, let's have some fun with our trees. Instead of manually building one, although we could, we'll use a fold to build up a tree from a list. Remember, pretty much everything that traverses a list one by one and then returns some sort of value can be implemented with a fold. Shit, folds. I don't feel confident with folds at all. So I guess it's a good thing that we're reaching the folds. I'm just thinking that I'm a little bit tired. It's the end of the stream and maybe we should wait on the folds for tomorrow. We'll see. We're going to start with the empty tree and then approach a list from the right side and just insert element after element into our accumulator tree. Oh. Oh, right. No, it's what we did, right? We just insert into tree. And we just take our accumulator value. We don't change anything, we just insert it to the tree. So we insert 5, we insert 3, we insert 7. Actually, I'm a little bit curious. What happens when we get to, what, 4? Where does 4 end up? Oh, no, right. No, it works. Because 3 ends up on one side and 4 ends up on the other side from 5, yeah. Right, these are our nums. Let nums tree, fold right, tree insert. We're gonna insert empty tree nums. Oh, right. Because we insert a number and we always have to insert the empty tree as well because that's what it takes. Left and a right. Notrunner says, I've seen this video many times, but I can't stop watching it again. Yeah, I'm gonna watch it later. I mean, it's starting to look good, right? It's one of these things that are just super satisfying to look. It's a little bit epileptic, I guess, but yeah, I'm definitely watching that later. Yeah. satisfying stuff. Alright, and then we do nums tree. Right, we call it. We create it and then we call it. And this is our tree. Oh man, I wish you could get a visualization of this. Well, actually we do, right? This is our left side, this is our... Is it? Yeah. This is our left. This is our right. It's a little bit difficult to spot, but... Right, just like here, it's 3, so this is our left, and this is our right. And that's the left tree done. And it's the same over here, right? This is our right tree, and this is our left off the right, and this is the right off the right. That's fine, yeah. In that fold right, tree insert was folding function. Yeah, tree insert was the folding function. It takes a tree and a list element and produces a new tree. An empty tree was the starting accumulator. Right, yeah. That's the starting accumulator. Exactly, empty tree. But then it becomes 5, so we insert 5. Nums, of course, was the list that we were folding over. Indeed. When we print our tree to the console, it's not very readable, yeah. But if we try, we can make out its structure. Yeah, it was a little bit messy. We see that the root node is 5, and then it has 2 subtrees, one of which has the root node of 3 and the other 7, etc. 7 3 elem in nums tree. All right. Nice. Did we create this function? I don't remember, but yeah. Checking for membership also works nicely. Cool. So as you can see, algebraic data structures are really cool and powerful. Are a really cool and powerful concept in Haskell. We can use them to make anything from Boolean values and weekday enumerations to binary searches, binary search trees, and more. Yes, very powerful indeed. And that is it for today. We will continue with type classes tomorrow, probably. Unless I do, miss out again, but that's fine. Alright, but that's it for today, so thanks for hanging out, and yeah, have a good one. Cheers.